Today's presentation features a project from the University of Wisconsin-Madison and the University of Iowa, and I'm pleased to welcome our presenters, Simone Benatti from the University of Wisconsin-Madison and Chris Schwarz of University of Iowa. I'll turn it over to you. Thanks.
Thanks, Jacob, for the introduction. Good afternoon, everybody. Thanks for being here. So I will talk about this project of interfacing Synchrono and NADS. So let me first introduce what Chrono and SynChrono are. So Chrono is a multi-physics simulation library. It's implemented in C++. It's open source on an extremely permissive license. It features support for a variety of physics problems, but we will focus on a subset of these that are of our interest. Speaking of Chrono vehicle, which is the Chrono submodule to simulate vehicle dynamics. It is template based, meaning that each part of the vehicle is defined separately, like suspension, steering and mechanism, suspension mechanism, powertrain, and each one of these is defined either in the code or with a easy to use JSON file. And these are put together in a vehicle system that, as I mentioned before, is composed by a set of subsystems and used to model a vehicle that uses Chrono to simulate its dynamics. As a side note, the subsystem also allows for co-simulation if need be. Together with this, we also provide a set of predefined models. So if someone wants one of the predefined Chrono vehicle models, can use one of these. These are the civilian models. We also have a bunch of military models and also track vehicles. These are not just nice visual assets, but each one of these models also provide the physics system definition for all the subsystem of the Chrono vehicle model. Extremely interesting in this set of problems, so it's also our sensor simulation tools. Sensor simulation is a kind of recent addition to Chrono. It features proprioceptive sensors, so sensors that are based on the vehicle physics, such as the IMU, the DDS, speedometer. And together, we also have exteroceptive sensor, so a sensor that sense the surrounding. These are simulated in a parallel process running on the GPU and based on the ray tracing sensor optics, in particular optics 7. And thanks to the sensor simulation module, we can simulate camera, lidar, and soon radar that are almost baked. So if the user wants to run an autonomous stack that uses sensor data, it can just use sensor data coming from our sensor simulation. So now we talk about Synchrono. Synchrono allows for distributed simulation of Chrono vehicles. So each Chrono process that simulates a vehicle, and obviously the sensor, because we cannot have control without sensor, in a virtual world, can interface with another vehicle simulated in the same virtual world, but on a different process. So in other words, we have a bunch of Chrono process that simulates one or more vehicle, but a few vehicles, because of course we are limited by the hardware resources. And each vehicle can control either by a human or by an autonomous stack. And this vehicle can interact with other vehicles thanks to Synchrono. So in Synchrono, we call rank a process that contains an agent. Actually, it could be more than one agent, but for sake of simplicity, let's assume that each Chrono rank contains exactly one Chrono agent. And let's assume that an agent is a vehicle, even though it's any controllable entity. To be either a robot or a traffic light. Let's keep it simple. So we have different ranks that are basically simulation processes that can interact with each other thanks to Synchrono Communication Layer and exchange information about their agent. So what we do in a more specific way is exchanging the vehicle state such that each process, so each rank, is capable of reconstructing the vehicle in its own process, such that the sensor, so the LiDAR, the camera, can sense and perceive these other vehicles. There is no physics interaction, so we cannot, for example, simulate the contact between two vehicles, but we're not interested in this. We are more interested in having the sensor being able to perceive the other agent simulating on other ranks. Of course, this allows for multi-agent scenarios like this, in which we are able to be faster than real time while simulated up to 128 vehicles at the same time. And more recently, we also improved our SCM simulation, so we can also simulate up to 27 vehicles while simulating also the formable terrain, even if it is not exactly the case of this case study. Specifically for this project, we also added to Synchrono a DDS communication layer. So it's basically a communication layer that is an alternative to the MPI communication layer that we've seen before. DDS has a few advantages. So the first one being the dynamic discovery of participants, meaning that whenever a DDS process spawns, it starts to look for other DDS participants, and if a set of conditions is met, then it starts to add that participant, and if need be, listen to the participant. I said listen because there are publisher and subscriber. So a publisher is a DDS participant that publishes data. I brought here thoughts, and a subscriber is a DDS process that listens to data. The real asset of DDS, and the reason why DDS is being adopted by ROS2, is the quality of service. Quality of service is a set of settings that can be adapted to the particular hardware or protocol underlying the communication, like it can be shared memory on the same machine, or the local network, or even the internet, or even satellite communication. So even the DDS, thanks to quality of service settings, can adapt to a huge variety of communication situations. So it is more flexible, and it has a wider range of applications compared to MPI. The drawback is that it's arguably lower level, so there are more things up to us user to set manually. So back to, and this was actually done with MPI. So in this example, we see 13 vehicles, one simulate, one controlled by a human, and 12 controlled by simple autonomous that are run on our HPC infrastructure that is called Euler. I'm gonna start. So let me go fast on this. So we are capable with Synchrono on our HPC infrastructure to simulate a fleet of vehicles at the same time, each one of those running on autonomy with sensor simulation, full vehicle dynamics. Okay. As a side note, Chrono has also been interfaced with CARLA. CARLA is a well-known tool for car simulation, and now it is an alternative for physics simulation, so an alternative to physics for simulating car vehicle dynamics. So the car that you see here is running in CARLA, but underneath is using Chrono vehicle to simulate the vehicle dynamics. In addition, we are exploring the deep reinforcement learning. So we are using Chrono in the deep reinforcement learning context, so basically a deep learning process for control based on trial and error. This was made possible by PyChrono, which is basically an alternative API that uses Python and interfaces directly with our precompiled Chrono libraries. Thanks to this, we achieved interesting result of navigation with obstacle avoidance based on raw sensor data. This is and this is similar, but in this case, we're following a convoy. I'm gonna go fast on this because this is more context on what Chrono is and what it's capable of. Last but not least, we're also providing a sandbox so that a user can use our ROS2 sandbox, test, for example, obstacle identification or path planning algorithm. Can go in and test and use it in our ROS2 because, as you may know, ROS is extremely modular, so it's easy to take out one piece and add another. And as an ongoing process, we are going to interface Chrono with AutoWare, which is an industry standard but open source for autonomy stack. So in this case, the sensing will come from Chrono sensor. AutoWare will take care, be the brain, and take care of all the control of the stack. So we take in sensor data and put out actuator that we go back in Chrono and control our Chrono vehicle. So I've been introducing Chrono and SynChrono and see what its strengths are in the context of autonomous driving and vehicles and dynamics and vehicle simulation in general with sensor simulation and the hooks and tools that it provides in this context. Now I leave word to Chris and he will talk about NADS and what those guys are doing.
Okay, thank you, Simone. So the entire pipeline for dealing with automated driving systems, automated vehicles that Simone just presented is mimics very closely, the testing and design and testing, validation pipeline that a lot of folks use, but what it's missing is human in the loop simulation. And with human in the loop simulation, we can add on the important human factors work and other types of work that require a human in the loop in order to see how drivers interact with their automated vehicles. And so this Safer Sim project was a collaboration, between Wisconsin and us, where Wisconsin worked on the Synchrono aspect, and we worked on linking the Synchrono vehicle into the simulator. And that Synchrono simulation was a replacement for the NADS traffic vehicles, not the own ship. So you may, if you're familiar with the NADS, then you know that we run our own high fidelity vehicle dynamics called NADS Dyna. And in a future project, we may look at replacing NADS Dyna with an instance of Chrono. But in this project, we looked at replacing NADS traffic vehicles with instances of Chrono. And so the difference in fidelity there is like orders of magnitude between the very simple dynamics and controllers that our normal traffic vehicles use. Go ahead. So this project is one of a line of research that we've done on connected simulations, distributed simulations, really going back like 17, 18 years, something like that. The NADS one itself is already a distributed simulation. We call it a co-simulation because it is distributed amongst several computers with a scramnet low latency network that connects everything. What's different in some of these more recent projects is we're trying to connect to different simulators for various purposes. And unfortunately, we've used a different protocol for making that connection for each of these projects. And so this one, we used DDS. Actually, on the NADS side, we use the RTI implementation of DDS. And Simone is using the eProsima fast DDS, and they talk to one another just fine. But in other projects, we've used VR Link with DIS and different implementations. So interoperability between simulators is still very much kind of an ad hoc affair, even though there are these standards out there that can help you a little bit. So we implemented that, and this slide just shows a little bit more of a background on the simulator and the center. One of the reasons that we're interested in this connected simulator technology is not only to connect NADS-1 with other simulators, but we have a growing fleet of instrumented on-road vehicles, the latest of which is a Ford Transit instrumented an automated shuttle that we're using for the ADS for Rural America project. And this shuttle was instrumented by autonomous stuff. It has a automation layer with a ROS component. And so there are pipelines here using DDS. DDS is used in ROS 2.0. And we will have an opportunity in the coming years, I hope, to begin to interface the simulators with the instrumented on-road vehicles. All we have to do is really nail down this infrastructure to do the connection. And so this project was a really great step forward for us. And we also really enjoyed taking advantage of the software that they're developing at Wisconsin, adding in the sensor simulation, and we think that NADS can really benefit from that as well. So what we're going to play now is a video of our interactive drive that Simone and I did, where I'm in the NADS-1 dome and I'm driving and interacting with a vehicle that Simone is driving, very much like you saw them drive on that mini sim earlier. He's driving the other vehicle, and now he's going to overtake me. So this is a networked simulation. We're communicating over the DDS layer. And that vehicle, from the perspective of my software, looks like a traffic vehicle, even though it's actually another human in the loop. We could also just supply computer-controlled agents from Chrono or SynChrono and feed those over the network and to populate our network as well, our simulation, that is. So that just shows you kind of our proof of concept upon which we can build all kinds of future work. So you want to take it back, Simone?
Sure things. Thank you, Chris. So here I'm gonna show how we connected Synchrono and NADS more from our perspective, and the result will be obtained. So the first obstacle to overcome has been that we wanted not just to interface Synchrono and NADS, but to interface Synchrono running on our HPC infrastructure, the computer cluster Euler. Euler is an HPC infrastructure that provides several compute nodes equipped with modern GPU and CPU, being powerful for specifically for high performance computing. But it comes with a problem. So if the compute nodes, so the node on which the simulation runs, cannot be directly interfaced to the external world. So all the communication has to pass to the head node, which is the node of the computer cluster responsible for the communication. This obviously is a problem, but it also has a few benefits, meaning that since we have this single node that takes care of all the communication between Iowa and UW-Madison, we need a single firewall exception. So for a single IP, so the IP of the head node is the only IP that NADS interfaces to, and then any other simulation performed on any other machine under the network of UW-Madison, that can be my personal workstation or other compute nodes or the driving simulator on the third floor, they all communicate with NADS through Euler head node. So this is difficult, but also at some point very convenient. There's a single publisher and subscriber going on between Euler and NADS. So this is faster in terms of sheer performance. And as I mentioned, the umbrella head node means that the head node of Euler manage the communication between NADS and any machine that on which we are running Chrono simulation. So we end up having two different DDS communication layers, one between NADS and the head node, and one between the compute nodes and the head node. They might interfere, so we have to take care that we don't step on each other's feet, meaning that DDS shouldn't subscribe to, for example, the compute node should not subscribe to the topic going on between NADS and Wisconsin. And they also, but this is also an advantage again, because during this double layer, we can have different quality of service. What does this mean? Well, in other words, it means that we can have more strict requirement in terms of communication on the internal nodes and relax a little bit when we have to communicate over the internet. So this is a representation of how the things work from our perspective. We have a head node that acts as a fake Synchrono rank, and a bunch of other proper Synchrono ranks that might run on my, as I said, on my workstation, or better, that's what we did on Euler workstation. And they communicate each other, communicate each other their state, and most importantly, the rank, the Synchrono rank on the Euler head node does not simulate anything, but it keeps trace of all the state of all the agents simulated on the Euler compute node. So what this node does is transmitting all this data into a single message that is sent to Iowa, and getting back the Iowa vehicle state and pretending that it's just its own agent. So this is how it works. This is the message that we send to, and we send and we receive from Iowa, which is called vehicle set, which is a clock. It has a clock called sample time, and an array of data. It's one of these is a called vehicle type. The vehicle message is carries an ID, so the ID is an increasing number. Type, because we can have different type of vehicles, for example, the sedan or stuff like that. Light state, we did not use. Body and a set of tires without pose. Poses are again another custom message that defines position, rotation, and their derivatives. We also implemented the reckoning. That reckoning is a strategy that we used whenever we had a message that was behind the time of our simulation. It does not happen often. So luckily we are, the communication is fast enough to not use that reckoning a lot. But whenever this happens, so whenever we find out, we check that the time of the client is behind the time of the server, what we do is basically doing Euler integration and guessing the pose in the next state. Whenever we get back a fresh message, we just use that. So in this simulation, we have one vehicle that was driven by Chris, and it is overtaking two Chrono vehicles. These two Chrono vehicles are simulated on an Euler compute node. So we wanted to stay simple for this demonstration, but since we are interfacing NADS with the Euler HPC infrastructure, we could aim higher than that. So we could have we could have more vehicles than two, and each one of these is running a simple autonomy. But we plan to have something more sophisticated in the future. So in a moment, the NADS control car will overtake the second Chrono car. So this is the scene reconstructed from the Chrono simulation point of view. As you see, the assets are different, but this is just because we define that in a different way. Of course, we can put on the map the post coming from Iowa, whatever asset we want to. So here we have one human in the loop vehicle simulated in Iowa interacting with these two autonomous, simple autonomy vehicles simulated on our AQC infrastructure. While this was obtained by simulating one vehicle on NADS and one vehicle on our simpler simulator here in Madison, Wisconsin. As I mentioned before, again, we are not simulating this time, we're not simulating the vehicle on Euler, but the communication is still running through Euler head node. So this is the advantage that we do not have to go crazy making a whole autonomous section for each different machine to which NADS interfaces to. So as I mentioned, what we are planning to do in the short term is improve consistency. As you maybe noticed, the wheels are fixed with respect to the chassis. It's something that is basically already taken care of, and improve the performance, because right now we can simulate more than 2 vehicles, of course, on in this experiment, but we want to go way higher than that, talking about 20, 30 vehicles at the same time interfacing with the NADS controlled vehicle. More in the long term, we want to run a full autonomy stack on each one of these Chrono vehicles. I said it is a byproduct because we are already looking into this, so this will happen anyway. And at that point, when we will have a full working interface between a proper autonomy stack and Chrono, it will just be straightforward to have it working in this current example. And more complex practice scenarios that will be made possible by a more intelligent control. In the long term, what I foresee and I hope to see for this trust is having extremely complex and open scenarios in which we can have different human in the loop using the National Advanced Simulator together with simpler simulators. It can be even just a steering wheel joystick connected to a workstation, and different kind of autonomy, such as more into standard like AutoWare or some homegrown autonomy in the development phase that we want to put there and see how it works and how it behaves. And even in terms of hardware, something that we actually already achieved because we are already doing this. We are interfacing simulator, complex cluster type, cluster-based HPC infrastructure and workstation. We are already doing that. So that's how I see things in the future. Having a single complex environment in which any user can interface and test his own under development autonomy stack, or maybe just go there with this simulator or simpler just workstation plug into which you plug a wheel and pedal and see how it behaves in that scenario. Thanks for your attention. I hope we have a few minutes for question and answer.
All right, great. Thank you, Simone and Chris. As Simone just mentioned, we do have time for a couple questions if there are any. Feel free to type those in the chat box, or if you'd like, feel free to unmute yourself and you can share your question that way. While we're waiting for questions, I will remind everyone that this presentation will be available on our YouTube channel and website within the next couple of days, and we will send that link with you all directly once it's available. Please feel free to share that with any colleagues that may be interested. We do have a question that came in from Rich Romano. When was the MPI or HLA used?
Well, MPI is now is an alternative to DDS. So for this project, we had to use DDS because the problem was that we couldn't start simultaneously the head node communication and communication on the compute nodes. So this started as a problem, so we cannot just use MPI as it is, and we had to use DDS instead, which turned out, as I mentioned, to be an advantage because now with DDS we can do all sorts of crazy things, like using Mario Station, using Mario Simulator, or connecting to the other head node. So MPI was not specifically used between NADS and Synchrono because we basically the communication over the internet we cannot use MPI, and internal communication we could not coordinate MPI exec to MPI exec to work with the head node communication. What is HLA, by the way? Sorry.
I don't think we used HLA either.
Okay, I thought I saw one screen where HLA was mentioned. Sorry if it
Maybe it was human in the loop, so it was human in the loop.
Oh, okay. I misremembered. Thank you.
No problem.
Awesome. Okay, well, we do have Simone's email on the screen. I know you can find Chris's on our NADS website. I will also include their emails when we send this link around. So if you do have any follow-up questions or comments, please feel free to reach out to them directly. And I will mention our next webinar will be November 16th, and that will feature a project from the University of Iowa's Hank Lab. We will send more information about that here soon. So with that, I'll end it here today. Thank you again for joining and enjoy the rest of your day.
Thank you. Bye.
Thank you.